नमस्कार दोस्तों, आपका स्वागत है हमारे YouTube चैनल जेके एकेडमी इंडिया में। आज हम ट्रांसफार्मर के तीसरे चैप्टर को स्टार्ट कर रहे हैं। इसमें हम ट्रांसफार्मर के नो लोड बिहेवियर को समझेंगे। तो चलिए शुरू करते हैं। ट्रांसफार्मर ऑन नो लोड। A transformer is said to be on no load when secondary winding is kept open and no load is connected across it. As such, no current flows through secondary. I2 is equal to 0. Hence, secondary winding is not causing any effect on the magnetizing flux set up in the core on the current drawn by the primary. But the losses cannot be ignored. At no load, transformer draws a small current I0, usually 2 to 10% of the rated value. This current has to supply the iron losses, means hysteresis and eddy current losses in the core, and a very small amount of the copper loss can be neglected, okay, because I2 is also 0. Therefore, the current I0 lags behind the voltage V1 by an angle phi 0 called the hysteresis angle of the advance, which is less than 90 degree. So I0 has two components. One is IW as shown in this figure. IW is in phase with the applied voltage V1 called the active or working component. This is IW. It supplies the iron losses and small primary copper losses. Other component is the I magnetizing in quadrature with the applied voltage V1. This is the I magnetizing, and reactive of magnetizing component. It produces flux in the core and does not consume any power. So this is the circuit where we have applied V1 voltage, I is the magnetizing current, phi m is the flux produced in the core, E2 is the EMF induced in the secondary winding, and this is the waveform showing phi m I magnetizing, no load current and voltage of the transformer. This is the equivalent circuit of the transformer. V1 is the applied voltage, I0 is the total current, IW is the active component, and I magnetizing is the reactive component to produce the flux. E1 is the primary induced EMF, E2 is the secondary induced EMF. So we can say IW equals to I0 cos phi 0, I magnetizing equals to I0 sin phi 0, and the power factor at no load will be cos phi 0 IW upon I0 from this equation also. No load power input will become P0 equals to V1 I0 cos phi 0. Exciting resistance will become R0 V1 upon IW, and exciting reactance will X0 will be X1 I magnetizing. Effect of magnetization on no load exciting current. A transformer requires less magnetic material if it is operated at higher core flux density. Therefore, economic point of view, a transformer is designed to operate in the saturating region of the magnetic core, although it increases the harmonics in the wave. When the voltage applied to primary of the transformer is sinusoidal, then the flux set up in the core assumed to be sinusoidal. The no load current I0 exciting current will be the sinusoidal due to hysteresis loop, which contains fundamental of all odd harmonics. So the behavior of magnetization or the effect of magnetization on no load exciting current is also shown in this graph plotted against phi and I. As we have seen in BH curve graph, the BH curve was plotted against magnetic flux density and intensity. Here it is drawn against phi to I, and this is the sinusoidal waveform which represents the equivalent behavior of this magnetizing current and the uh, uh, flux phi as well as magnetizing current waveform. This is the I0 waveform and this is the flux waveform. So here both are in the same time frame, means there is some small lagging, not much more. Okay, so you can read this also. uh, the above current is required to be modified on account for the AD current loss in the core, and the modified current is called the no load current I0. The corresponding current component, apart from being phase with applied voltage V1, is sinusoidal in nature, and it balances the effect of sinusoidal AD current caused by sinusoidal core flux. It is therefore seen that AD current do not introduce any harmonic in the exciting current. However, eddy current loss reduces the angle between applied voltage Vi and no load current I0. It is seen that the waveform of no load current contains third, fifth, higher order odd harmonic which increase rapidly in maximum flux is taken further into saturation. However, the third harmonics in the predominant one. For all practical purpose, harmonics higher than third are negligible. In no load current, the third harmonic is nearly 5 to 10% of the fundamental rated voltage. However, it may increase to 30 to 40% when the applied voltage rises to 150% of its rated value. When the load on transformer is linear, the sinusoidal load current is so large that is swamp out the non-sinusoidal nature of the primary current. Therefore, for all the practical purposes, the primary current is considered sinusoidal at all loads. In certain three-phase transformer connection, third harmonic current cannot flow. As a result, the magnetizing current is almost sinusoidal. For satisfaction of BH curve, the flux phi must then be sinusoidal. It is flat-topped wave. This can be verified by assuming sinusoidal magnetizing current and then finding out the flux wave shape from the flux magnetizing current relationship. The normal magnetizing curve, neglecting hysteresis component which is in phase with V2, since the flux is flat topped, the EMF which is its derivative will now be peaky with a strong third harmonic component. The various waveforms are illustrated in figure. So this is the third harmonic waveform having less magnitude compared to induced EMF, and this is the fundamental waveform. This is the flux waveform. Flux is flat shaped, not purely sinusoidal, and this is the magnetizing current. Under load condition, the total primary current is equal to phasor sum of load current and no load current. Since the magnitude of load current is very large as compared to no load current, the primary current is almost sinusoidal for all practical purposes under load conditions. Thus, while operating in saturated region, the magnetizing current contains more percentage, that is 30 to 40% harmonics. Now, inrush of magnetizing current. When a transformer is initially charged, there is a sudden inrush of primary current. The maximum value attained by the flux may reach to twice of the normal flux. The core is driven for far into saturation with the result that the magnetizing current has a very high peak value. For mathematical treatment, let applied voltage V1 equals to Vi sin omega t plus alpha. Here alpha is the angle of voltage sinusoidal at t equals to 0. Suppose for the moment we neglect core losses and primary losses, V1 equals to N1 d phi by dt. N1 is the number of primary turns, phi is the flux in the core. At steady state, V1m will be omega phi m N1. Phi m the maximum flux density, and because here you can see phi is the phi m sin omega t. After differentiation we will get omega phi m cos omega t, and for maximum cos omega t equals to 0 equals to 1. So V1 maximum equals to omega phi m n 1. Now n1 d phi by dt is equal to this, as we have seen in last, and this is d phi by dt. Now d phi by dt will be omega phi m sin omega t plus alpha. Integrating, we get phi equals to minus phi m cos omega t plus alpha plus phi c. Where phi c is the constant of integration, the value can be found from initial condition at t equals to 0. Assume the assume that when transformer was last sinusoidal, uh, sorry, assume that when the transformer was last disconnected from the supply line, a small residual flux phi r remained in the core. Thus at t equals to 0, phi equals to phi r. Substituting this value, we will get phi r equals to minus phi m cos alpha phi c. Phi c is equal to phi r plus phi m this. So here are two terms. One is phi m cos omega t plus alpha, and second term is phi r plus phi m cos alpha. This is called the steady state component of the flux, and this is called the transient component of the flux. Now these two equations shows that the flux consists of two components, as we have discussed. The magnitude of transient component phi c equals to phi r phi m cos alpha if is a function of alpha, where alpha is instant at which the transformer is switched on to the supply. If transformer is switched on at alpha equals to 0, then cos alpha is equals to 1, and phi c will be phi r plus phi m. Under this condition, phi equals to this, and omega, when omega t equals to pi, then phi equals to 2 phi m phi r. Thus the core flux attains the maximum value of flux 2 phi m plus phi r, which is over and above the twice the normal flux. This is known as the doubling effect. Consequently, the core goes into deep saturation. The magnetizing current required for producing such a large flux in the core may be as large as 10 times to the normal magnetizing current. Sometimes the RMS value of magnetizing current may be larger than the primary rated current of the transformer. So here you can see this is the total value of flux produced. It is 2 phi m plus phi r, and this is the waveform of V, and this is called the transients, and this is the normal magnetizing current. This inrush current may produce electromagnetic forces about 25 times the normal value. Therefore, the winding of large transformers are strongly braced. मतलब वाइंडिंग को अच्छे से टाइट किया जाता है. Why? Inrush current may also cause improper operation of protective devices like unwanted tripping of relays, momentarily large voltage drop, and the large humming due to magnetostriction of the core. Magnetostriction of the core. To obtain no transient inrush, phi c should be 0. So this should be 0. Then cos alpha will be minus phi r upon phi m. Since phi r is usually very small, cos alpha equals to 0. Therefore, alpha equals to n pi by 2. In other words, if the transformer is connected to supply line near a positive or negative voltage maximum, the current inrush will be minimized. It is usually impractical to attempt to connect a transformer at predetermined time in the voltage cycle. This is the game of millisecond, so it is not possible. Fortunately, inrush currents do not occur as might be thought. The magnitude of the inrush current is also less than the value calculated by purely theoretical consideration. The effects of other transformer in the system, load current and capacitances all contribute to the reduction of transients. So thanks for watching. ये था ट्रांसफार्मर का नो लोड बिहेवियर and how the transient was produced in the transformer core at no load switching.